So this course, so we will be talking about multiphase microfluidics. So there are two different terms in this course, multiphase and microfluidics. So multiphase generally refers to different phases, gas, liquid or solid. So a case where there are more than one phase is present and the flow happens, that is what we call multiphase flow. Now the other term is microfluidics. So in microfluidics we are looking at flow at a micron size scale or small scales. So when we say microfluidics, it is not necessarily that the flow is only at the micro channel. It is, I refer to this microfluidics is basically flow at small scales. So the first question that comes to our mind, why to study this? With the advance in manufacturing technologies, there are number of microfluidic devices or small scale devices that are being developed. For example, in biomedical applications, you might see that to measure the sugar level, one just need to pierce a needle and take a small droplet of blood, and then one can tell the sugar content of the blood. So these are called lab on a chip devices. Then in the inkjet printing, where the channel size is small and the exact amount of liquid needs to be dropped, the exact size of the droplet needs to be generated, and then it has to be spread on a paper and dried in a very small time scale. Then another application is microreactors. So people are talking about now that the size of a plant can be reduced, say 5 to 10 times by using microreactors. Electronics cooling is another application where people are looking at the two-phase flow or boiling applications to remove the very high heat fluxes that are being generated by the electronics. And microelectromechanical system, there are a number of microelectromechanical devices. So all of these devices generally involve multi-phase flows. There it's not necessary that it is only one phase flow, either air or water or only one liquid, but there are a number of different phases flowing together. So of course one need to understand the physics at the small scale in order to be able to design these devices efficiently. In addition to that, all the flow systems in our body or in biological systems, they are all at micro scale, and the fluid that flows in them, they are not simple single phase fluid. For example, blood has in a liquid there are number of particles, different size of particles suspended. Similarly, when the flow happens in lungs, the size of the alveoli is small, they are few microns only, and there is two-phase flow. There is gas, particles suspended in the gas, as well as the walls of all the alveoli and the entire system, entire pulmonary system, they have a liquid coated on it, which is generally called mucus. So to understand the physics of biological system also, we need to understand the multiphase flow in microchannels. Now how it is different, or what becomes different when we talk about flow at small scales, few hundred microns, say for example. So one of the things what changes in size is surface area to volume ratio. So if you have a 1 meter diameter pipe and the surface area to volume ratio, or if you say that surface area is proportional to L square and volume is proportional to L cube, so the surface area to volume ratio is proportional to 1 over L. So if the this quantity is about 1 for a 1 meter pipe, and for 1 millimeter pipe this quantity becomes 10 to the power 3, and for 1 micron pipe it becomes 10 to the power 6. So as the size of the channel is reduced, the surface area to volume ratio becomes high. So now what happens that the forces which are negligible at large scales, the surface forces, they are negligible with respect to the volume forces at the large scales. They start becoming important or even dominating at the small scale. One of the examples, or very common example that we will talk about in this course, is surface tension or interfacial tension force. So that might not have been very important for the flow in large scales, but that is important for the flow in small scales. So in this course we will look at the different flow regimes that occur into gas liquid flow in microchannels. So one of the differences is that there is no stratified flow, because the role of buoyancy is decreased, which is a gravity dominated or volume dominated force, and there are different flow regimes, for example bubbly flow or slug and Taylor flow, annular flow. So the two flow regimes which are very important in microfluidics is slug or Taylor flow and annular flow. So we will look in detail the shapes of the bubbles or droplets, say for example in liquid flow, and the film thickness, the velocity of bubbles and droplets, and so on. We will also look at inertial microfluidics, which is that the when you introduce the particles in a channel, the particles settle at a particular radial location or a particular transverse location, because that is the equilibrium position for the particles. And this has found a number of applications recently in a number of biomedical or lab-on-a-chip devices. So we will look at the physics of inertial microfluidics. We will also look at briefly at the experimental or measurement techniques, for example microparticle image velocimetry, and the computational technique to model such multiphase flows, for example volume of fluid methods. So who should take this course? The final year undergraduate students who has done a course on fluid mechanics, and if they have done a course on multiphase flow, even better, or the postgraduate student and research student who are interested in the area of microfluidics or in the area of multiphase flow. This course will be beneficial for them and for their research.